Start. Okay. Welcome everybody to this Methods Hub seminar. Thank you so much for joining us on this afternoon during the summer. So I'm really grateful that you could turn up for Dr. Lam Ming-Long's seminar on Shapley values. I'm very, very grateful for Dr. Lam to come and to talk to us today on aspects of his work that he's been working on for a very long time. So Dr. Lam comes to us with a lot of industry experience. So he's been working in data science in commercial institutions and in SPSS and SAS. So these are, very, very famous organizations, as well as in retail and banks as well. So he specializes in algorithm developments and with an emphasis on statistical learning. So he received his PhD in statistics from UChicago, and then he's gone on to work in this really important commercial institutions, and then more recently joined the Data Science Institute at the University of Chicago. So he's a full stack data scientist. I'm not quite sure what full stack means, but he's a completely bona fide data scientist, a software developer, and an educator as well, because he's written a couple of books on data science. So please join me in welcoming Dr. Lam and thanking him for his presentation.
First, thank you very much for inviting me. It is my pleasure to speak at the Hong Kong U. This is before it started. It is some of the things. It is he just mentioned it. What is a full stack data scientist? Literally, in American we have all kinds of great names like full stack, wall to wall, ceiling to floor. Basically, it means there's anything in between. Yeah, completely. So the full stack data scientists, including things like I can know how to pull the data in, I know how to do SQL, I know how to do data analysis, I can write program, I can do analysis, presentations, and so basically it's anything from the beginning to the end. Yeah, so basically it's like if you think about it's a kitchen, I'm the one that actually wash the vegetable all the way to the waiter. Yeah, so you can see that is the full stack. Yeah. What I know about Eric, I call him Eric. You guys call him Dr. Fong. Yes, Eric Fong, because we are in the same cohort of the University of Chicago student when he was studying at the sociology and I in the statistics. Yes, we call PATH. Yes, and then I personally know his wife too. So let us go into the Shapley value. Yeah, first of all, is people will understand what is a Shapley value. Spoiler alert, Shapley is the name of a person. Yeah, so you know that is named after a person. So what does it do? First is usually most of the talk they would dial in the math thing. This is not the way it is U Chicago. At least in my program, we don't dive into the math. Yeah, it is my teacher will teach in that way, but we teach in try to explain what this Shapley value it is. So I start with an example: share a taxi ride in Chicago. Yeah, I'm sure you have the experience of sharing a taxi ride. Yeah, probably not in Chicago, but in anywhere. And then one of the things after you share a taxi ride, there is always a big problem. How much should I pay? Yeah, you don't want to pay more, you don't want to pay less, you want to have the fair share. So we start with actually this example. So since I'm not very familiar with the taxi system in Hong Kong, so I use the example in Chicago and also let you to see what is the Chicago landscape look like. Suppose we have three students, I call it Betty, Amy, and Kathy. Yeah, rather than to just name them person ABC, I call them name. Yeah, this is also the American way. They don't just call a person ABC. We give them names. So after the meeting, after they have a capstone project meeting at the Griffith Center, they want to share a taxi ride. But Amy want to shop at the Water Tower Place. Betty want to join the family at Lincoln Mars Zoo. and Kathy have a baseball date at Wrigley Field. They agree to share a taxi ride. And of course, it is Wrigley Field is the last stop, the destination. So Kathy will pay for the fare first, and afterward they will Venmo back into to Kathy. Yeah, I'm not sure if you know what is Venmo. You know how the American student work. Yeah, they don't pay cash either, but they don't have autobus. Those they do Venmo. So that is the landscape. The route it is Creature Center as the bottom. Yeah, you can see it is a satellite campus of the University of Chicago. It is next to the Chicago River, a very scenic area. So if you have been to the U of Chicago campus in Hong Kong, so you know that U of Chicago have a tradition of picking campus at a very scenic location. And then Amy want to stop at the Water Tower Place. It's only a short distance from it, do the shopping. And then Betty want to go to Lincoln Park Zoo. This is the one of the zoo in Chicago. It is somewhere in the middle, halfway between, and finally Wrigley Field. It is the home of the Chicago Cubs. Yeah. So they are going to, that is the taxi ride together. So what it is, how long is the trip? 5.1 miles. Yeah, because we are the imperial system, the country is about 82 kilometers and lasts 27 minutes. And at the end, the taximeter showed $28.48. And we also pay tips. Yeah, it's quite different. It's in Hong Kong, I pay tips, and then the waiter will say, we come back, they say, sir, you lost some money, you forgot some money. Yeah, you should give it. Yeah, I say, no, we pay tips. So in Chicago, even if you take taxi, you have to pay tips. The standard rate, we call the standard rate is 80%. Yeah, 80% of the tips. And Kathy pay everything by $33.60 by credit card. So what is the fair share? So we look at what is the Chicago fare system. Yeah, when they pull the flat is $3.25. Each additional mile is $2.25. Each 36 second is 20 cents. And first passenger, they cost $1. Each additional passenger, they cost 50 cents. And if you pay in credit card, you have to pay 50 cents. Yeah. And of course, the other two doesn't apply to them. Yeah, they didn't get out of the bar, so they don't have to clean up the vomit. They don't, if you take the taxi from the airport, they will charge you $4 more. But this doesn't apply. So can we just, one of the things is, can we just divide into three parts? Probably is not, because one of the things we noticed that is the fare depends on the distance. Yeah, and from the picture, you can see it is Water Tower Place is pretty close to the Creature Center. Lincoln Park Zoo is a little bit farther away, and Wrigley Field, it is the furthest. So you cannot just divide by distance. And also, the number of passengers is different. Yeah, because we have 3 passengers in here, but if Amy do it by herself, only 1 passenger, the price is totally different. Yeah. So because of the number of passengers and an equal distance, we cannot just divide in it. So think about it is more like a model. You think about it's an equation. So the fare is a function of the distance and also the number of passengers. Yeah. So you cannot divide it. Yeah. So what is the fare solution will you suggest? Yeah. If you cannot divide by 3, what is the fair share? Shapley Value, at first it is developed by economists. So they are not from a statistician. From the economists, they have to think about it is what is the fair share, what it is. I don't want to pay less because Kathy doesn't want to collect less money, but at the same time, you don't want to pay more than your fair share. What is in there? Yeah. So we will put it on the side. Yeah. At the end, it is a solution that you can use it not just for taxi ride. It's also very good for when you're sharing a meal. Yeah, you eat the fish, you eat a little bit more. You order a drink. Okay, we can talk about it. Second example we are talking about is more as a regression model. It's a predicted contribution to a linear regression. Yeah, often that it is in all the model, we fit a linear regression model. We have the coefficients, we have everything there, but each of the predictors come in different scale. Yeah, some is measured in inches, some is measured in thousands of dollars, so the scale is different. So we cannot just look at the coefficient because you can see it's by changing the scale of the predictor, you can change the coefficient. Yeah, so you cannot just look at the coefficient, bigger coefficient, smaller coefficient. So you know that the thing is there. So how do we do it? But another bigger problem, it is when some of the predictors are linearly dependent. Yeah. So we go through a hypothetical data. We have only 7 observations, so we can actually see it. The target variable is y. The predictors are x1 and x2, and it's not difficult for you to see that x2 is actually equal to minus 1.1 times x1. Yeah, you can see they are totally linearly dependent. Yeah. So if we run a linear regression using x1, yeah, you can do it very quickly. Either use R or actually you can do it by hand. Excel can do it, no problem. This is the equation 1.5 plus 0.9021429 times x1, and the R square, that is the coefficient determination, is 0.9619. Yeah, it is a pretty good R square. Yeah, because I make it up, so it is a very R square. So if we put the linear regression using x2 as the predictor, then the equation will be different. But the R square, if you can remember what is the previous slide, then you will see the R square basically is the same. Yeah, if you have some background is the linear regression. Basically, it is if x2 is actually is a mathematical function of x1. Actually, you can calculate. Given the x1 regression, the coefficient, you can actually easily get it into the x2 coefficient. And we will say, well, if you put multiple linear regression, if you put x1 and x2 also as a predictor, needless to say, we know that it is one of them will be found as a redundant. Depends on which one you go first. If you put x1 first, x2 will be redundant. Usually the software will put the last one because they check the redundancy from the beginning to the end. Yeah, usually that is the common convention. If you put x2 and x1 first, x1 will be redundant. Yeah. And then we have 2 linear regression equation, but the R square is the same. But as we see, it is, although the equation looks different, we can actually recover another equation without refitting the regression. We can just have do some kind of linear algebra. So we have 2 equations, looks different, but actually the R square is the same. Now the question is, if we put x1 and x2, and then we look at which predictor is more important or what is the contribution, most of the time we will have a dilemma. Depends on which one you put in the name first. Yeah, whether you put in R, SPSS, or SAS, they will ask you what is your predictor, and the way you put it, that is the way the software think that x1 is you want x1 first. So we check, and then x2 is the second. So we will check the redundancy with x2 last. But at the same time, we also understand that the R square are the same. So if the R square is the same, that means both of them give the same goodness of fit value. Yeah, regardless of how you measure it, whether you do the coefficient determination or you use the F significant value, anything that related to model, they're the same. And if people say, well, you have to pick one that is important, we try to break the tie by name. Yeah, you will find out that it is kind of not quite, it's not a good idea. Just because your name comes first doesn't mean you are more important. Yeah, often says the students say that is, my last name starts with A. Is it more important than the student that starts with Z? Yeah, it depends on what the student asked, what the teacher asked for. Yeah, if the teacher is thinking about to assign F to the student, the one with A is not very good. Then you think, okay, let you do first. On the other hand, if other things, then the one with the start with Z maybe is have certain benefit. So we cannot just resolve this tie by the name. Should we do it? We have a gut feeling that they should be equally important because basically X1 and X2, they are the trend. We call the numerical trend. Yeah, they are just you can easily replace X1 by X2, X2 by X1. Yeah, so you cannot just say because the name is one X1 and X2, that differentiate the importance. They should be the same. But how do we know that they are the same? Okay, the third example. I'm sure when you study high school math or elementary school math, you have this example before. Inflating a swimming pool. They will say, well, you have a swimming pool. If you have 3 pumps, pump A can inflate the swimming pool alone in 21 minutes. Pump B can inflate alone in 15 minutes, and pump C can alone in 9 minutes. If all 3 pumps work side concurrently, how fast can we inflate the swimming pool? Yeah, really, some kind of the memory come back. Yeah, that kind of question. When I took the elementary school, it's very hard. Afterward, you find that it's not that difficult. Yeah, some of you still remember it. So we say that it's supposed that V is the required air volume for the kiddie pool. Yeah, regardless of what it is, the unit. Is this cubic feet, cubic meter? It doesn't matter. It's a V. And then if we have to ask for 1 minute, what each of the pump can inflate. So A will inflate V divided by 21, B inflated by V over 15, and C will be inflated V over 9. So if they work all 3 together, we will say, well, in 1 minute, they can inflate the sum of it. Yeah, so it is here. So if they have to work together, how fast they can inflate the kiddie pool is V divided by the sum. So since it is positive, we cancel out. Afterward, we figure out is 4 minutes and 31 over 71 minutes. Yeah, it is not difficult, at least for our level, yeah, to work it out. So the question is, which pump contribute much more? How much, say, like the kiddie pool is inflated? What it is, each pump, what is their contribution? Yeah. Well, we know that the C work the fastest, B is the second, and then A is the slowest. So it's qualitatively, we can talk about their contribution. But quantitatively, how do we decide their contribution? Yeah. Or put it another way, it is if we say what is the numerical portion of the swimming pool that is inflated by each of the pump at the end of those 4 minutes and 31 over 71 minutes. How do we do it? So we start with, it is share the taxi ride. We can have linear more as a statistical problem. What is the relative important contribution in the linear regression? And finally, we have an air pump. How do we measure the importance of variable in a regression model? Yeah, because in here, it is actually, you can express as a regression model, E2. So the feature important, yeah, often that it is a feature important. It is a very common buzzword is in machine learning. Okay, which feature is more important? Yeah. I always ask the students, say, what do you mean by important? They say, what? What do you mean by important? They actually ask me is this, we use the word important without thinking, what does it mean? Yeah. So important here, but not there. Importance is a relative concept. Yeah, before I check out some of the things. The yeast, time, international driving permit, numerical target variable, a target variable. Some of them, it is, when you think about, say, yeast, is it important? People say, yes, it is important. We have to use yeast to make bread. Time, of course, when you drive a car and airplane, when you don't have time, a car without a tie is a very big 9,000 piece of paperweight. That's it. You can't useless. Yeah, although it is a Tesla, it's still useless without the tie. International driving permit, I found is that you have to drive this permit. If you travel to Japan, you need this international driving permit. Numerical variable, we need for linear regression. Yeah. If you ever try to run a linear regression with a qualitative target variable and then just recode them 0, 1, 2, 3, I'm sure your professor will give you some lecture. Yeah, what is this? A target variable, we call the supervised model. In machine learning, there is a jargon called a model with a target variable. It's called supervised. But things are the same you think important is not important another way. If you try to make cake, you don't need yeast. Yeah, you need baking powder or baking soda. You can't make, if you try to make cake with yeast, your cake will be very hard. Yeah, some are still, when we're a graduate student, and Eric tried that. Turns out that we make cake, and turns out that it's the yeast. It looks like bread. And the tie, if you're driving a boat and a ship, what's the point of having a tie except as use a bumper when you try to park the ship? International driving permit, you don't need it. It's not important. It's good to have, but you don't need it. You're driving in Illinois, USA. All you need is Hong Kong driving license. You can drive it, yeah, for 90 days. Yeah. Well, numerical variable, it is useful in logistic regression, but we don't need to know that they're numeric as long as we know that they are categorical. And if you have a target variable and then you try to fit an unsupervised model, they won't say that it is wrong. They just don't care that whether it exists or not. So important is some kind is a concept. Yeah, relative to what you are doing, and also the context. So we think about it as we can evaluate its important if we specify a feature. We can evaluate its important if the model include it. Therefore, it is just like the example we have is if X1 is in the regression model, we can talk about all kinds of importancy, but can we discuss its importance even if the model does not include it? The question is, doesn't include it. Yeah. For example, like there is Messi is a very famous soccer player. He recently came to Hong Kong. He didn't play at all. He just sit there. And then, of course, you know that he will collect a lot of money, even if he just sit there. He's not paying anything. You cannot say that he is not important to the team because if he is not there, people in Hong Kong will not even go there to yell at him. Yeah, unless when they met at the team, they will say because they met a Messi, because Messi is there. If Messi is not there, of course, people don't even care about that team anymore. So the question is, if the model does not include a variable, can we say that it is important? The question is here. So how does the usual in the linear regression, how do they evaluate important? This is the statistic side to do it. They will say, well, train the linear regression model any way you want. Second, after that, it is a backward elimination. You remove one feature from the model and you calculate the change in the coefficient of determination. And then use an F-test to check whether the change is positive. Yeah. We'll say that if a variable is useful, then they say if you remove it, the R square will go down. And of course, people will say, well, the one that have the biggest change in R square is the most important. But since it is, the R square is this, we think that it's everything from 0 to 1, but well, the R square change, although it may be a very small one, but if the original R square is already very, very small, it does mean something. So we cannot just use the change in R square. We have to use some kind of F-test to use a certificate to check on it. And the statistician, usually after you do the F-test, they calculate the important as the negative of the base 10 logarithm of the F significant value. Yeah, we will see in a moment is how do they do it. Suppose it is some of the math in here, okay? Suppose the model, the regression model have P number of features. Yeah, whether it's categorical, it doesn't matter. We are talking about one feature is one feature. And the model degree of freedom is M0. Yeah, this is the number of non-alias parameters. Yeah, the word non-alias seems to sometimes may be foreign to you, but is basically is the number of non-redundant parameters. Yeah, they is in statistics is they in a field called general linear model. They have the concept of alias. Aliasing basically is the same. It's a very fancy word for dependency. Yeah. Well, the coefficient of determination is big R0. So, okay, suppose we remove the J features and we retrain the regression model. And the model degree of freedom is M minus J. Yeah, the minus J indicate that the J features is gone. And then the coefficient determination is R squared with a subscript of minus J. So the test is like this. It is R squared 0 minus R squared minus J divided by M0 minus M minus J divided by 1 minus R0 divided by M minus M0. Okay, the formula seems very complicated, but if you have some of the math, basically is that it is the F-test for backward elimination. Yeah, if you are familiar with regression, we do the backward elimination. This is the F significant for removing one variable using the backward elimination. So, and then we calculate using F distribution. After we have the F statistic, we calculate with a F distribution with a pair of degree of freedom. And since we already know that is removing a feature will never increase the R squared. Yeah, is always the truth. So we know that the F statistics is always positive. After we calculate in here, so why we use the significant as a measure for important? We go back into the definition of what is the F significant. It is, if you remember the statistics class, they talk about type 1 and type 2 error, type 1 error. The type 1 error, it is say like, if the null hypothesis is indeed true, and then you do not accept it. Yeah. So literally, it means it say like, if the model say that the null hypothesis say that there's if you remove a feature, there is no change in R squared. Yeah, when say no change in R squared, we are talking about the population, and then you ignore it. Yeah. So that means it is you are committing a type 1 error. So we already know that it is when we reject the null hypothesis, we just check the significance. Is it less than 5% or not? Yeah, this is the 5%. We put aside why we have the 5%. Yeah, that will be another lecture on it. It has something with something called the Fisher. At a certain point, people ask, what is the threshold? He just say, well, okay, 5%. And because he says so, it lasts for 200 years. Nobody ever challenged him. Even after he's dead, nobody ever challenged him. So the smaller the test significance, it say that it is more evident to support the conclusion that R squared has increased. Yeah, because it means the smaller significance, that means the type 1 error is very, very small. So even if we say that the R squared indeed is no change, we do not accept it, that error is very, very small. So we will conclude that, well, in that case, we just reject the null hypothesis anyway. So the smaller the significance, that indicates that it is more safe to reject the null hypothesis, or in other words, to say that the R squared did change. So with a p-value significant, it's very small, it's very hard to deal with it. So what we do is we just take the base 10 log and then attach a minus sign. Yeah, that one have nothing to do with anything statistical theory. It just make a very small number to be a big number, positive. That's all. Yeah. So we look at this example again. Yeah, remember x1 and x2 are linearly dependent. So if we put in the this data, we put in another categorical variable. I forgot to mention it. We put in a categorical variable called negative, 0, and positive. And of course, you know that they are kind of related to x1 and x2. If we fit this one with categorical x1, and then we try to remove s, the categorical, the F significant value is 0.4310. If we try to remove x1, it's 0.0120. Yeah, because it's knowing the sign of the x1, it helps to determine the y, but not as strong as knowing the actual value of the x1. So if we take the important, we take the base 10 of the significant and then attach a minus sign to it. So we can tell x1 it is more important. This important is a relative value. Yeah, it is basically say we compare to 0, since it's 1.9219 is further away from 0 than 0.3656. Yeah, all we say is further away from 0, we cannot say that it is 6 times more important. No, we can't say it's relative. So we say that x1 is relatively more important than s. Everybody agree it? We try x2. Since x2 literally is x1, if I put a different shirt on that, so we are not surprised to see that the important base it is the same as the previous one. So if we do this, we think, oh yeah, it's good. Let's put the x1, x2 together. Then I'm sure they, if we remove it, they will tell us in there. Unfortunately, we put in there, we cannot do the F statistics. Yeah. The reason is this: if you take away x1 from the model, x2 will just step in. Yeah, it is as if x1 have left the model. If you take out x2, x1 will say, I'm coming in. Yeah. So in that case, the R squared will not change at all. Yeah, if the R squared will not change, then we cannot get the F statistics. If we cannot get the F statistic, then we cannot get the significance of the importance is NaN. It is a convention in Python to say that we cannot compute the number. So with this one, then the question is, what's wrong with the model? We thought that is a way that we can evaluate the importance, and turns out that this is a way that we cannot evaluate either important at all. Now suddenly S becomes the only important thing because I am the only variable that you can have an important value in there. So of course it is, if you load statistics, it's very easy because it is S0, it is an X1 day alias. Yeah. We call the S0 is called the intrinsic alias because it is by construction of the categorical variable S, because you have create dummy variable. And X2 we call the extrinsic alias because it just happened alias because of the data. Yeah, it's not by construction. Most of the time we see alias is intrinsic. We make a mess. So we get into the traditional way of using the significance as a measure for importance. It doesn't work if you have predictors that are linearly dependent. Yeah. So what do we do? So it's a good time that we will introduce Shapley value. And in order to do the Shapley value, we have to introduce you something called a coalition game. So game theory, it is part of the game theory. Yeah, game theory, you don't have to worry about what it is. Basically, it's a branch of math. They talk about it is people do have a strategy, and then how do they get the biggest payoff? Yeah, if you have experience playing video game, basically you are practicing game theory every day. Yeah, but in game theory, the player, we call the self-interest player. So each of them, they have their own strategy, they have their own payoff. But different from video game, you don't need to kill the player. Yeah, video game is you want to eliminate them, but in the game theory, you are not to eliminate them. And for each of them, they have a choices. That's what we need is to know. It is just like in the predictor, in the linear regression, each of the predictor, they have one choice to go in and out. Yeah, when they go in and out, everybody have to make a choice. Yeah, you cannot have a predictor say, I'm not in, I'm not out. You ask, what are you? In the game theory, there is something called the utility. Utility. It says that it is there a numerical value that represents the level of benefit of a profit. So they make a choice, they will have positive, 0, or negative in there. Yeah. So you can say it is like if a predictor is into the model, it will raise up the R square, or it will not change the R square at all, or if they get out, they will have a negative utility. Yeah. And then the utility function basically is just a mathematical function. So all we need is to some of the basic concept of game theory. What is a coalition game, or we call the collaborative game? First of all, each of the player we call the coalition. Yeah, if you think about, if you have ideas of playing soccer, basketball, basically that is a coalition game. It's all the player will form a coalition. Their whole goal is, first of all, although each of the player will make their own decision, whether to pass the ball, shoot the ball, or whatever, their main goal is they want to, as a team, they want to increase the playoff. Yeah. But some of the concept about the coalition game, you can have a coalition with no player. When you have a soccer field, they have nobody in there. That is a coalition with 0 player. And of course, when there's nobody in there, everyone knows that there's no score. Yeah, that's a common thing. So, but in the Shapley Value, their focus is on, we call the grand coalition. It's not just any coalition, it's the grand coalition. The grand coalition, it is a coalition when all the possible players are there. Even though if Messi, it is in the coalition, he is not on the field, he is part of the grand coalition. So for each of the players in the grand coalition, they demand a playoff. And what is the fair share? So the whole thing is about, in Shapley Value, it is how to allocate the playoff of the coalition in the grand coalition. Yeah. Well, time to show who is the Shapley. It is Dr. Lloyd Stowell Shapley. Yes. If you know is in the economics, you probably know his name already. Yes, he is a mathematician. His PhD dissertation is 1953, A Value for N person game. This is where he developed the Shapley value. And then he waited almost 60 years, 59 years to be exact, to get the Nobel Prize. And unfortunately, after 4 years, he passed away. Yeah, so getting a Nobel Prize actually takes a long time. Yeah. But the Shapley value as a summary, overall view, it is it gives you an absolute importance for all the predictor considered for the model. It's not a relative, it's an absolute. Yeah, it's an absolute. When you say it's a relative, absolute, the thing is, this relative important is depends on what is your model. Your relative to your current model. The absolute is say that even though if the variable is not in the current predictor, we can still calculate the important. So the important is not tied to any particular model. Yeah, it's not tied to any particular model. That is why we call it absolute. Yeah. How the algorithm will say that it is, we will consider all possible sequence the predictor can enter into the model. Yeah. And each sequence generates one realization of the model. And then we will average out all for each of the realization, we calculate some kind of importance value, and then we take the average. And then the average is the Shapley value. Yeah. Somehow it is very hard to grab what is the concept. We go for this, but we will go for each of the example. But before that, I show you the math. Even with the math, you are even lost. What is that? Yeah. So basically, it say that it is first that you have a utility. You have a utility, you have a coalition S, the big capital S. Now you include the player I, you minus the utility without the player I, and then how many ways you can form this coalition with S and the player I. You have N minus 1 over S way to do it. You sum it up, take the average, done. Yeah, this is from his dissertation in there. Yeah, this is a formula. Of course, this is in practice, nobody actually implement it this way. Yeah, nobody implement it this way. So what we are going to do, in the interest of time, let me jump directly into the example. Yeah, let's start with the taxi. Yeah, we have the Amy, Betty, Cabby. You still remember Amy get off at Watertower Bridge, the first one to get off, better in Lincoln Bus, the second, and Cabby is the last one who paid the fare. So what are the information we need to calculate the Shapley value? We need the value that if they ride by themselves, one, if they ride by alone, if they ride in a pair, Amy or Betty, Betty or Kathy or Amy or Kathy. And the third piece of information is when they all ride together. Yeah. So we go and figure out using the our Chicago taxi scheme of fare. So we look at it is for Amy, it's only $10.69, including tips. Yeah, actually in Chicago, in Hong Kong, the taxi fare is much, much cheaper than in Chicago. Yeah. In Betty, it's $29.68 and Kathy $32.42, etc. Yeah. So at the end, we know that when they all three together, it's $33 and $60. So we have, those are all the information we needed. Yeah. Later on, you will find out why we need it, because basically we are doing is an all possible subset model. Yeah, basically this is the all possible subset. Yeah. Except one, of course, is if nobody take the taxi, what's the fare? Should be zero. So we will have the utility value. So we will say if Amy by itself is 1068, if B by itself 2068, if C by itself 3242, and then we have each of the pair. Each of those are the utility value. And then how many ways to form the grand coalition? Is 6 of them. Yeah, 6 ways to form it. Yeah, 3 by 2 by 1. Yeah, it's not 2 to the power 3. It is in there. So the possible sequence, it is ABC, ACB, etc. All 6 of them, we can eliminate. We can list them out. After we list them out, first we create a table. It's like this. We'll say list out all the coalition, and then we will have the player. We say what is the first player join it, second player, the third one. Because each of the Amy, B, ABC can start a grand coalition. Yeah, they have no restriction say you can start it. So when Amy started first, we call that is the first player. So that is in here. And then if Betty joined it, then the coalition value is 21.27. And if Kathy joined it, 33.60. As you can see, is I already color coded. So Amy have the red color, Betty have the green color, and Kathy have the black color. So you can see is for each of the player join, what will be the utility value of the coalition, not that person, is the grand coalition. Yeah, for that coalition, not grand coalition, that coalition. Next, now we have to break it down into each of the player contribution. So for the first one, we say, what is the Amy? You can see also color-coded. Well, Amy started, well, she is the first player, so it's 1068. Yeah. When Betty joined it, the coalition value, it is 21.27 minus 10.68. That is the contribution of Betty to the coalition. So it is $10.559. And finally, Kathy will say, well, when Kathy joined the last one, after he joined, he did get 33.60 minus the coalition before the Kathy joined. It is 21.27. So we got 12.33. So from here, so for the first table, we look at what is the value of the grand of the coalition when a player joins. We don't need to know which player, but afterward we have to know Amy, Betty, and Kathy. Depends on whether in each of the sequence, whether they are the first player, second player, and third player. Yeah, you look at that, you can very quickly. You can. I only say it's difficult. Yeah, actually, it's pretty easy. You can do it in Excel. So at the end, we have for Amy, for each of the sequence, we have 10.68, 10.68, 0.59, 0.59, 0.59, 0.59. We just take the mean of that. It sums up to 23.72 divided by 6 is 3.95. We also look at Betty. The mean it is 8.95. And for Carrie, the average contribution 20.70. So we can see it is, I highlight it. If you look at the screen, if you look there, you can see it is what it is, which number, where the number graph from. Yeah. So afterward, you will see that it is the Shapley value of the taxi fares example. So Amy is 395. Betty, it is 895. And Carrie is 2070. One of the things is in check whether our calculation is correct is we add up all the Shapley value, it will equal to 3360. Basically means it is if you add up, you have to equal to the final share, total share. Yeah, you cannot be 1 cent more or 1 cent less. So we check the calculation and make sure all the Shapley value equal to the utility value of the grand coalition. Yeah. From there, we also break it down into percentage. Yeah, the percentage is the Shapley value divided by the total, the sum of those three values. So we can see that it is Carrie pay roughly 61.6% of the fare. Betty is 26.6% and 11.8% for the Amy. Yeah. So this is one example. Yeah, so it is, you can use it. I'm sure you can apply to the next, anytime where you have dinner with somebody else. Yeah, it will make you look smart. Let us look at some smart Shapley value before we actually pay for it. Okay. But the second example, it is the swimming pool. Yeah, we have the swimming pool. We can go a little bit faster. It is, but we have a problem. It is because it's what is the utility value? Because we have to choose a utility value. For the example before, the taxi fare is simple, the fare. The more people, the higher the fare. But if we use the minute to inflate the pool, it's not good because the more pump, then the minute actually go down. It is not what the Shapley value say that you can't do it. You have to find a utility function so that the more pump you have, the higher the number. So instead of using the minute, we use the rate, how fast the pool will be inflated. Yeah. So we use the rate, then we know that if the pump only is A pump only, 1/21, if B pump only, 1/15, the C is 1/9. And if we have A and B together, the elementary math tells us is the sum of 1/21 plus 1/15, etc. Yeah, so this is pretty straightforward to do it. Then we follow the thing it is the taxi fare. We have the pump ABC. Yeah, so the first place join is for the ABC. When we start the pump A is 1/21. If the pump B join the collision, it is we add 1/15 to it. If the C come in, we add another 1/9. Yeah, we look at the math. You find out that we don't actually need to resolve it because actually you just add up the sum. And if we now is go back is to find out what is the contribution of each of the pump. We just minus take the difference between the sum. You figure is this, how come pump A is all 1/21? Pump B is all 1/15 and pump C is all 1/9. Literally, it just say that we already calculate the pump Shapley value by just knowing how fast each of the pump work individually. So the Shapley value for A is 1/21, for pump B is 1/15, for pump C is 1/9. those are the Shapley value, and then we can get some of the percentage in here. Yeah. But what do we know about this one? Why we don't have to go through this very complicated thing like the taxi fare thing? Because it's the pump, they do not cooperate. Yeah, it's not saying like the pump A, the pump B come in and say, oh, the pump A is all working, I will work faster. The pump B will not. The pump B will just work as it is what pump B will do it, same as pump C. Because in here, the utility, it doesn't depend on anything. It just depends on whether the pump is there. Yeah, it's not like the taxi fare. The taxi fare depends on the utility, depends on number of passengers in there, how far they travel, etc. You will have some kind of cooperate. They will collaboration together. Yeah, because it's like if Amy and Betty work in the taxi, first of all, they will, because of one additional passenger, they will bump up the fare. And also, Betty go a little bit further away, they will bring up the fare also. It is as if they cooperate together. Although it is conceptually, they cooperate. But in this case, the pump didn't cooperate. They sort of work independently. So we know that is for some kind of model when we know that the predictor, they do not cooperate together. The Shapley value basically is just an addition. Yeah, think about if you have variable that are is totally independent. They have zero correlation. Yeah, they don't cooperate together. Let's look at this final example. How many, first of all, we have to look at it is the all possible subset regression is that for p number of predictor, the number of possible subset is 2 to the power p. Yeah, 2 to the power p, because it is like the binomial theorem. If you remember something is called the binomial theorem, it is basically the expansion of 1 plus x to the power n. So if we have 3 predictor in there, the number of regression model we can have is 2 to the power 3. We get 8 of them. We start with the one with intercept. Intercept plus s, intercept plus x1, intercept plus x2, etc. For each of the regression, we fit it and then we get the R squared. Yeah, so you know that we need to fit quite a lot of regression model in here. Once we get the regression model, so then we go through it is what is the first player, second player, third player come in. Look at, we mark down the R squared. Yeah, it is a tedious, but you just double check your work. And from the R squared, then you know, okay, which one is S, which one x1, x2. Yeah, you can see some of them is 0. Yeah, for example, like what is the second one, the second row? X1, oh, sorry, the X1, it is 0 contribution because X2 is already there. Yeah, when X2 is already there, you add X1, the contribution is 0. Yeah, because it's, in this case, the X1, the software will not allow X1 to be in at all. So we have all the contribution. Now we take the mean of it, and then we got the Shapley value. So in this case, we notice that the x1 and x2 have the same Shapley value to indicate that in the grand correlation, x1 and x2 are equally important. And we also get this percent Shapley value. And how do we break it down? The interpretation is first we can talk about the R square. You can say, well, the whole model account for 97.8% of the variation of the target variable y, and about 26% of the variation in target variable y is accounted by S. 35.7% of the variation in target variable y is accounted by x1 or x2. So we did this how we accounted for. So the interpretation is that it's not to say that they are important. There we just say what percentage of the variation in y is accounted by that variable. Yeah. Or we can say it is the percentage. We can say it is as it is among the Shapley value. Well, is the weight. We can call about the relative weight in there. Yeah, we'll say, well, there are 0.38%. So we did this, we just use it to give us an idea as what is the relative size, because sometimes the R squared can be a very small number. So it's hard to give us an idea, okay, which one is the bigger one, which one is the smallest. So the percentage give us an idea, say, the x1, x2, a little bit in terms of the importance, they are bigger than the one in S. Although we will have, originally I decided there's a pop question in there. They say, well, if we do not consider x2 at all in the training, and because we know the dependency, what will be the Shapley value of S and x1 in the regression model? Some people will say, okay, if x1 is not there, okay, basically say, well, we have a piece of cake, my twin brother doesn't want it, I take it. So people will say, well, in that case, that S will be the same as 0.2844, and then x1 will just take it. Another one is 0.70. You think that is, if I don't take it, the other will pick it up, S will be in there. We think so. And the turns out it's not. Actually, it's different. Because we forgot there is a collaboration between S and x1. Yeah, we often forget that you have beside x1 and x2, there is the S and the categorical variable S and x1, they also work together. Yeah, if x2 is not there, x1 will pick up some of the thing, but S will also pick up some of the thing too. Yeah, you just say, S cannot say that you can't have the cake all by yourself, you have to share some of it for me too. Yeah. So it is an explanation to it. Well, in the interest of time, I would try to jump into how do we calculate it. Well, nowadays there are usually two channels. One is using the Python or R. Yeah, for the Python, there is a library. Yeah, but I usually prefer my own. So if you are interested, you can contact me. Yeah, and also how to work on it, and also I left a copy of the Python code with this group, and you can contact whoever it is in charge to how you can get it. But you have to know some background about Python. But if you are not sure how, I don't know how to run it, you have problem, contact me. But if you are in the R user, then you can just call the Shapley value in R. The value is called Shapley value, and you can get it from this website. Yeah, it is still actively used, but they are more they use the R squared for the general linear model. Literally is basically means a regression with categorical variable too. So if you are using the R sample, first you create a data frame. Yeah. And then you specify factor as a categorical variable. And one word it is, you cannot use a variable called x1 because the Shapley value object, the library, they use it internally, they use a variable called x1. Yeah, I learned it my hard way. I tried so many times. I put x1, they complain, say that you have duplicate name. I say, what is duplicate name? I don't have one. And until you read the code, you say, okay, you use x1. So do not name your variable x1. Yeah, you can name anything except x1. So if we define the train data and we will fit a linear regression, in R is pretty simple once we set up all the groundwork. The LM function we got the R square at 0.9782. And also we see that the second variable, basically that is our X2. The R, we say that it is the estimate is all NA because they found out that it is linearly dependent. Although R will say that one is, they just say one is not defined because of singularity. So it's hard to tell what is meant by one not defined because of singularity. Yeah, because basically it's a linear dependency. But if we run the S, first we load the Shapley value, and then we just put in what is the Y and what is the X. Yeah, they do not accept the formula. They take what is the Y, they also give you a matrix of X. When you run it, boom, that is the only function, only output they have. That is the Shapley value of factor 1, factor continuous 1, continuous 2, and also the standardized Shapley value, it is what I call the percent Shapley value. They add up to 100%. Yeah. And also it is they hard-coded with only 4 decimal. It doesn't matter whether you say in our option 13 decimal, they still print you 4. Yeah. It is an unfortunate thing in there. Yeah. So you can run in R. If you are very comfortable in R, all you need is download the library and make sure that you have the R version is compatible. Yeah. If you use the Python, that is more flexible because you can choose any utility function you want. Yeah, you don't want the R square, you can pick something else. And also you can also try out different kind of model, even with interaction. So about is a remark on the work on the interaction. If you have an interaction, the Shapley value will not, you can either think about as Shapley value as an interaction as one entity. You calculate the importance, or you can still break it down and say, what is the importance of each, say like this interaction x1 times x2. Yeah, you can calculate x1, x2 as by itself. You just divide x3 equal to x1, x2, or they will break out to what is the importance of x1 inside altogether, even when they appear as an interaction. Well, we look at the closing remark. The Shapley value will be, actually it's a good thing to evaluate the importance of features. Even for alias feature, that is a good selling point of it. Yeah, it doesn't have to say just because the features are linearly dependent, we cannot evaluate important. We can say that even if it's not there, what is the important? The second part is, it totally depends your choice of utility function. That choice is you. You like to have a coefficient determination, or you pick other thing. If you are familiar with logistic regression, you pick your own R square. Yeah, they have Mathern R square, they have Cox and Snell, you pick your own. Yeah, it is the one that you are comfortable with. Final word it is, you may heard about that, is another thing is called a SHAP, S-H-A-P. At first, you would think that, well, did you forget to spell Shapley? Some lazy person just don't want to spell Shapley. They call SHAP. Actually, SHAP is a different thing, related. It stands for Shapley Additive Explanation. With this Shapley value, one of the, I would say it is, we'll say it's a problem, but people is annoying, is when you have too many features. Think about 10 features. How many linear regression you have to fit 2 to the power 10? Yeah, with a computer this size, no problem. 20, okay, you start to have a bit more concern. Yeah, 20, probably you will need a bigger computer, more stronger. Yeah, and if 32, forget it. None of the computer can work on it. So, but often that we have 40. If what the SHAP will say that in this case, instead of actually calculate the Shapley value, we are going to approximate the Shapley value. Yeah, we are able to help you to go beyond the machine physical the limitation, because it's 2 to the power 32. It is an integer very big. Yeah, 2 to the power 64 is even bigger. So if we don't have the patience, or we cannot afford the time, we will just approximate. We not get the actual value, but getting approximate is better than getting nothing. So if you heard about something called a SHARP, that it is a machine learning way to approximate the Shapley value. And of course, if we can do it, then of course we will prefer the Shapley value. Yeah. So that is the end of it. And thank you for inviting me to speak. And you can contact me with the U Chicago email, or you can contact me with LinkedIn, and I'm also on the ResearchGate. So if you have problem with the outcome, or if you want to have some further discussion, feel free to drop me an email. Okay. Thank you.
Thank you. Thank you so much, Dr. Lam. And we have some time for questions. We will be putting up the slides and the video recording and the link to the Python program on the Methods Hub website. So yeah, so please do feel free to contact us or contact Dr. Lam afterwards if you need to. We definitely have time for questions, so please feel free to ask away. Given people are quite shy, I will jump in with one. I knew nothing about Shapley values before your talk, and it's one of the problems I often find with variables that are linearly dependent in regression models is, for example, I'm often interested in finding out whether combinations like average, if I want to put in x1, x2 into model, and they're different variables, then I want to put in an average as well, then the average is of course linearly dependent on x1 and x2. But I'm interested in knowing, is the effect of the average, is the importance of the average different from the importance of x1 and x2? And I can never find that out in traditional way because of the linear dependence. But it seems like the Shapley values method is giving me some way of establishing how important the average is compared to the component variables.
Yeah. If you take x1, you have x2, and then you take the average of it. That's two ways you can do it. Is either you define the average as a totally different variable called x3. And in this case, x1 and x2 doesn't know x3. They think that they are just some distant cousin in there. So in that case, then you have 3 variables. Then you will fit 2 to the power 3x of those predictors in there. And of course, some of them, the R-squared is different. So then you can calculate the importance of x1, x2, and the average. Or you would say, no, I don't want to do it. I want to see it is I add the average in there because I just want to have the model have a better fit. I'm not interested in the average at all. Then I still calculate the importance of x1 and x2. Yeah. So you would say it is, of course, the question is, okay, if x2 is not there, what do you mean by average? You would say x1 divided by 2. Well, this is a conceptual, there's a problem in there. But usually it is, we just define the average as a new variable. Yeah, and that the software will not know it. They will just do the job, but internally, the conceptual, you know that, okay, X3 is the average. So you can actually calculate Shapley value on that. Yeah, it is often that, particularly it is usually a common trick. They say when X1 and X2 are linearly dependent. So usually people say, well, take the average of it, and then another is take the difference of it. Yeah, because that it is literally is in the statistic is literally what we do is we are actually doing is eigenvalue decomposition. Yeah, but in this case it is we can't distort the regression, but as I say, is the regression the Shapley value is a 2. you can build the regression any way you want, as long as you remember what each of the variable in your regression mean to it. Yeah.
Questions? Yes, please.
Lam, thank you so much for your sharing, and I learned a lot from this. But I know later about the Shapley value, but in my study, I faced the linear dependency issue as well. So, for example, like age period cohorts or social status and social mobility. So I just put it into the statistics. So my X3 is calculated by the X1 and X2. So if we want to focus on the X3, so can Shapley value help me to identify the relative importance of X1, X2, and X3?
Yes. I think it's the simple answer is yes. It depends on how the X3 and X appear in the model. Yeah. If it's X3, it's just like it's a mask behind the scenes, the average of X1, X2, or they are actually totally in there. The Shapley value is, they call like correlation game, cooperation, collaboration. The form is a correlation. Means is when X3 come in, does it related to X1, X2, or does it help to bring up the regression model, the goodness of fit? Yeah. So what we are talking about it is you can have any number of features, any features you want. The goal it is the important is we will say, if the features is in there, does it help to bring the goodness of fit of the model higher, and what percentage it has contributed to X1, X3? Because it's when you have correlation between the three variable, when you have X3 come in, yeah, because X1, X2 are correlated to it. So when the goodness of fit increase, it may be actually, it's not because of X3, it's because of X1, X2. Yeah, they bring it even higher. So we want to have a fair share to calculate, say, what is the portion of the goodness of fit is attribute totally to X3. Yeah, that is the whole thing of Shapley value. What is the contribution of the goodness of fit of the model totally? It is due to X3. Yeah. Yeah.
Thank you very much. Question just for application property. We're only going to start what you see that the last one. The sharp additive explanation. The handle explanation given the same way as sharp with that. What are the portions? Sharp.
Mm-hmm. But the Shapley value that it can work for regression model, it can work for classification model, like logistics. The sharp is totally, it is a way it is to overcome the performance issue, for fitting a large number of a model. When the number of in machine learning it's very common to 100 features in there. Yeah, it's very common for our regression model. We know that if we fit 100 model, we know that we just commit suicide by ourselves. Yeah, it's no way we do it, because it's in our case it's a regression. We are focused is on the explanation. We just not just looking at the Shapley value. We also want to explain why it has a bigger Shapley value. Yeah, you go through the context of it, the sociological aspect of the variable. You want to explain why it has a high Shapley value. But in machine learning, they don't need to worry about it, or they want to know whether this variable is important, how important it is. Why it is important, it is not their concern. So they will put in 100 of them. And when you have 100 of them, they know the Shapley value will not perform. Yeah, in our machine learning jargon, it is we call it the dead on arrival. Yeah, 100, they are already dead on arrival. You can't even do it. So, but we want to do it. So they will have approximation. And they call the additive explanation It is because they know that it is how each of the features in the machine learning, when they add it to the model, how much they explain to it. So the name actually it is they derive it from Shapley value. They still calculates look like Shapley value, but instead of go through all possible subset, they kind of estimate. Yeah, because think about it, if you have 2 to the power 100 on those, we cannot fit the 2 to the power 100 regression model. But as long as we can approximate what will be the R squared. Okay, now if we get those all the R squared now, or that table, do the subtraction is a very big the table, it is doable. So all it is contribute is on how you get those approximation. Yeah. So the machine learning, the focus is different. Yeah, they don't need to worry about how to explain why it is in there. So they will very easily go to a very large number of predictors. Yeah. And also they use it as a way to screen it, say like, say the Shapley percent is add up to 100%, you have 1,000 predictor, and they will say, well, if you cannot make it, if the Shapley percentage is, you cannot even make it to 1%, you're out. Yeah, they use it as another way to screen the predictors out quickly. Yeah, rather than to, you can use some kind of model, but sometimes it will take a long time to do it. So they, besides the shape, there is other type of measure for variable important too.
Thank you, Professor Lam.
Welcome.
Thank you. And I'm new to this method, but I find it very interesting. And I'm curious about whether this method can be applied to nested data structure, for example, the multi-level data structure. And if yes, how does it work? It is work in the same way as the example you just provided. Thank you.
At the highest level, I would say is yes, because it is, they really don't want Shapley, Shapley the value, they don't actually want to know how you build your model structure. Yeah, all they want to know it is what are the variables in your model, how they interact, x1, x2, x3, the average of it. Shapley value, the calculation don't even care. Yeah, they don't really need to know. So you can do it as a hierarchical model. Yeah. They can calculate is the Shapley value in there, but now the explanation, it is on the burden. Because when you have hierarchy, certain variable will not exist until the upper hierarchy exists. So now you will be, the burden is on why the nested features have more important than the upper hierarchy. Okay, because it can happen, and now the burden is the explanation to you is why it happened. The Shapley value will just simply take care of the calculation. Yeah, so it can handle, and literally it can handle any kind of model, but the explanation is on the burden back to you. Yes. Sorry.
Okay, thank you, Prof. Lam, for your very insightful talk. And I have just a very quick question. I was wondering who was the guy that come up with this method who can use Shapley value to determine the importance of the predictors in this way? Yeah.
Well, the person is called the Shapley. Why it come back into it? It is, I think, it's some kind of good collaboration between it's not from the economists.
Yeah, but I've attended some lectures in microeconomics, but this is the first time I have seen that you can use this method to determine the importance of the predictors in the regression model, right? So I think there is like if it is first, maybe you can use this method to determine the marginal contribution of somebody in a group or something like that. But how can we like move that to this part to determine the predictors? But which one we should fit into the model that we can find optimal like performance, right?
Yeah, I cannot answer that is why something is from the econometrics is get introduced into it. It has to something with somebody is doing the linear for the I think is at the time the linear regression. How I introduced it, I was working on a project on insurance, and then they fit some kind of general linear model. And then they want to know which predictor is more important, what's the importance of each of them. And that is, I got introduced, and then I was given a paper to read, and then go figure out the math, how to do the implementation. That's all. Yeah. So I do not know why it's suddenly introduced, but once it's introduced, people find it's very useful, and then the sharp it is some of the extension in the machine learning side of the Shapley value, and we don't know how far this concept calculation will go.
But now it is a common practice in industry, right?
Yeah. There is R. They have library. Sharp. They also have library in there. Yeah, they have Python. Mostly is it if the Sharp is mostly in the Python. R, I'm not so sure, but in terms of the calculation, if you look at the code, yeah, if I have a chance, let me do some live demo. Yeah, because it's my talk description, they do some live demo. So it is a Python. Yeah. I'm using not just it is development interface is called the Spider. Yeah. In case you do not know how, say you are new to Python, how do you get it? First of all, don't just download Python from the web. Yeah, you do not know what you download it. Okay. We will prefer people to download it is. I don't have internet. Sorry. It is a website called Anaconda. It's spelled as ANACONDA.com. Yeah. It is a website. It is just like the R project. Yeah, it is the R project. They maintain a very stable distribution of the Python and all some other tool for it. This is a tool I call it the Spider. Yeah, it is a development platform. So if we go through a little bit, Python, it is just like R. Then you have to import the library. Yeah, you cannot. Some of them is already built in, so you will import it. And like in R, they have in the data frame. Yeah, actually, people will argue that the R actually copy the ideas of a data frame. They have a data frame, and then you will specify what are the categorical variables, what are the continuous. In this example, they all fit is linear regression. If you have a model, have linear regression, then you will just use it. And you have to enter the data. In the Shapley value, it doesn't take care of missing value. The missing value you have to deal with yourself, okay? What they will do is first, they will generate a data frame on all the possible subset of model. Yeah. We have a function. It is to say what it is the all possible subset. Maybe I will make it a little bit bigger. Yeah, that is the line. Yeah. Python, sometimes you will find out that is intimidating. Python developer tends to like to write everything in one line. Yeah. And in here, we have a data frame, so we can click on it. We can see that it is how we set up each of the predictor, okay, which is the position. So you can actually see that it's all possible subset. And then we have number of features, number of model degree freedom, because some of the variable is categorical. And then it has an R square. So afterward, how does we create all this? It is that piece of code, it is to run the all possible subset. Yeah. It is a long list. It is the loop. Yeah. In Python, when they run the loop, they don't like in R, they don't need to have the the curly bracket or the big bracket. Yeah. In Python, how do they determine the loop is by indentation? If all the lines is indent 4 character, then they belong to the same loop. If you find another line is indented 1 more character, they say it's another loop. So as a beginner Python user, you will be frustrated if you suddenly add 1 more tab and 1 more space, and they will say, well, there's no ending loop. Yeah, but those are something is very easy to overcome. And okay, that is the fitting the regression. And that is the part that also to find out which predictor, what is the contribution. Yeah. If you have the contribution, then here we go through it is something called the result DF. Then what we can look at for each of the feature, for each of the predictor, what is the feature, what is the R-square change, and what is the weight. It means is how many times this change should appear in the grand coalition. Yeah. This is mostly for internal, and afterward, then the rest is we just take the weighted average. So you have this degree of freedom, you can just basically say for each of them, you take the weighted average of the R-square. And then at the end, then we have the Shapley value. Yeah, it is, say it is S is 0.2644, X1 is 0.35, etc. And then finally is the percent. We just normalize it to the sum to a total 100%. Yeah, so if you are familiar with Python or you are willing to try it out, feel free to get this model. If you can actually get your data in there here, yeah, if you get the data in there, then everything will be fine. Yeah. The only thing you may want to is regression. How in the regression, how do they specify it? They will have a function called getDummy. They basically is from a categorical variable. They just create all the dummy variable for you automatically. Yeah, this is the part that you can maybe sometimes you be careful. So I encourage you, if you have a problem at hand, try it to see maybe it is a program that it is your first step to a Python. Although it will be a very big step to Python. Yes. If you have questions, do drop me an email, and we can talk, and we can think about it, and we can even write up some paper together. Yeah, I can deal with the Python part, but I'm not doing with the social science part. Yeah. Okay.
Thank you. Thank you for your patience.
Thank you. Thank you so much. Well, now gone past the time. So I've learned a lot from Professor Lam's seminar. I'm sure you have learned as well. I'm very, very grateful he's come to talk to all of us, and we learned a lot. And we've got code as well, which is wonderful. So finally, I'd just like to thank Professor Lam once again for this wonderful seminar. Thank you.
Yeah. Thank you.